Today's lecture is going to be on the formation and evolution of our solar system. Here, when we talk about patterns in the solar system, the emergent theory or hypothesis is that it formed out of a nebular cloud. This is a large cloud of gas and dust, about 75% hydrogen and 24% helium, that became unstable. The densest part began to collapse as gravity pulled the material toward the center of the cloud, as you can see in these animation pictures down here. A disk shape forms as conservation of angular momentum takes over. It flattens out the rotating body and allows for regions of space to become their own smaller scale accumulation of matter. This is where planets formed. The idea of conservation of angular momentum is kind of like this. There's internal forces or forces working inward of gravity that's forcing these clouds to collapse. But you also have gases expending or exerting pressure outward. Here, once the cloud begins to move internally and compress, it then begins to spin more rapidly. Here we see a kind of a counterclockwise motion. It's the same concept of what a figure skater, how he or she pulls his or her arms in to spin faster. As the material in the solar nebula collapses, this idea plays out. When generating angular momentum, it's important to look at what would happen if we push the skater's arms to see what would happen. Here, when pushed on the arms, we create what's called a torque, or a force that is exerted on the outermost region. But it differs, or it changes, if the same force is applied to the middle of her body, where she just falls over. A skater who starts spinning with their arms at their side cannot generate an increase in velocity. But a skater who starts with their arms wide and pulls their arms gradually in would increase their rotational speed as they bring their arms down and inward. So our solar system was born out of that contracting central location of the protoplanets as they're moving inward, as they're gravitationally picking up all the debris in their local field after the sun had already done its job of, let's just say, gravitationally collapsing the center of mass. And we get this fairly ecliptic plane, fairly flat, but it's definitely disc-shaped. And this is nothing more than the planets that are forming in the leftovers that didn't quite make it into building the sun itself. At this point, planets begin to differentiate or separate their material. The densest material sinks into the innermost part. Here's a picture of before differentiation. After it's differentiated, we get these layers, these internal layers that are distinctive characteristics of what's going on internally. The Earth is one large-scale density column, getting denser and really finding more iron as we travel inward. Looking at our solar system, we would find Mercury, Venus, Earth, Mars. These are the inner rocky or terrestrial planets. Then we have Jupiter, Saturn, Neptune, or Uranus, and Neptune in that order. Here are some compositional aspects or some values that we're going to find here, and it's going to be based on all of these objects that we find in our solar system. The distance from the sun, temperature, day and night, number of moons, number of rings, density, composition, revolutional period, rotational period, and the path of the orbit itself. Our terrestrial versus our Jovian planets, or Jovian, Mercury, Venus, Earth, Mars versus Jupiter, Saturn, Uranus, and Neptune. And here's a picture that better depicts what we're looking at here. We have these features of the solar system, and the features just tell us that the centralmost point is the sun. And we get our planets that are moving counterclockwise around it. And here's this Mercury, Venus, Earth, Mars, and then we have this asteroid belt. And we get into our Jovian planets, Jupiter, Saturn, Uranus, and Neptune. Remember, Pluto is no longer on here because it crosses into the orbital path of Neptune. Therefore, the Astronomical Society has defined or redefined what a planet is. It must be the largest object in its orbital sweep. So Pluto no longer gets that characterization of being a planet. And out here we have the Kuiper belt. And here's a document that you should have this in your lab, in the binder, of the different planets that are, well, let's just say the different characteristics of the different planet. And if you follow the columns, we can determine different planets by their symbol, by their AU, or astronomical unit, which is relative to the Earth being 1 AU, or 93 million miles, which is the same as 150 million kilometers. These are the period of revolution. These are the inclination, or how much they are off of the ecliptic. We call 0 the Earth. We call everything relative to 0 degrees from the Earth. Here are the orbital velocities in miles per second or kilometers per second. Here's the rotational period. Here's the diameter of the planets, or essentially the sizes of them. Relative mass, obviously Earth is 1 Earth mass. Average densities, you'll notice that the inner rocky planets are significantly denser. Saturn would indeed float in a container of water. It'd have to be a big bucket of water. And their temperatures. And we'll look at these a lot further in depth as we continue moving along. And last but never least, we get to rotation versus revolution. Remember, a rotation comes from an internal axis. A revolution implies that the sun is the external axis of which we revolve around. And there are 3 rules why the IAU, or International Astronomical Union, determines to be a planet. It must be in orbit of the sun, has sufficient mass to assume a nearly round shape, and lastly, has cleared its neighborhood, or is the largest body in its orbital sweep. And therefore, since Pluto crosses into Neptune's, it no longer holds that title.